Yes, good afternoon, everybody. I'm very happy to be here and certainly thank the organisers for inviting me to speak at this very interesting colloquium. I've really had a very enjoyable afternoon. Thank you to those in the room for staying until the very end. So I'm going to speak this afternoon on sustainable chemistry and hydrogen as pillars of the energy transition. And of course, I'm in the enviable position that a certain number of things have already been said this afternoon, but let me remind you, if I need to, that we have the legacy of 20th century use of fossil fuels, fossil fuel refineries, and that doesn't work. Fossil fuel refineries and all of the associated CO2 emissions, greenhouse gas emissions, CO2 emissions. And this diagram here on the left-hand side shows those CO2 emissions. Data from the International Energy Agency shows those CO2 emissions by sector. We can see that around 40% of those carbon dioxide emissions come from power, and around 46% between industry uses and transport uses. So our contribution then is going to be in the 21st century to e-refineries, and we were hearing about e-fuels in Mark's talk, to e-refineries and the harnessing of renewable energies. I'm talking this afternoon about the use of hydrogen and the use of hydrogen to store that renewable energy. And the use of the hydrogen in hard to decarbonize sectors of industry and also for transport. So we've already had a hydrogen fact sheet a few minutes ago. I don't need to spend very much time on this. I want to remind you it's the lightest molecule. It's the most abundant molecule. Of course, it's found bound up with water and in hydrocarbons. It's not as rare as we thought it was, perhaps, in natural form with white hydrogen. In the context of the energy transition, what's important is that its combustion produces only water, no carbon dioxide, and the gravimetric energy density is high. It's higher than that of other small molecules, alcohols that you can see there, other small molecules, and also higher than fuels such as gasoline, petrol, and diesel. So it's common to talk about the hydrogen value chain. So going from the production of hydrogen through the storage of hydrogen, through the distribution of hydrogen, and then its utilization. Once again, colourful hydrogen. I'll just take you quickly through this. We've seen the colours of hydrogen already. Hydrogen that comes from hydrocarbons, from coal, oil, natural gas, without carbon capture, brown, black, grey hydrogen. Blue hydrogen when we're using those hydrocarbon resources, but there is carbon capture and storage. And then yellow, pink, green hydrogen when the hydrogen comes from water by water electrolysis, using different types of energy, different types of electricity. Of course, hydrogen is completely colourless, so those colours have no physical meaning at all. And we prefer to talk about clean hydrogen, decarbonized hydrogen, low carbon hydrogen. At the present time, those low carbon hydrogens only count for perhaps not even 5% of the current hydrogen that's produced and used, and more than 95% then is this grey, brown, black hydrogen. And white hydrogen, then Alan just mentioned it, this very large deposit that's been discovered in eastern France, in the Lorraine area, but that's not the only region of France. In fact, also in the Pyrénées-Atlantiques and other areas in Auvergne, there are other regions where this natural geological hydrogen is being discovered, and certainly it's potentially something of a paradigm shift in the whole hydrogen scenario. So back to our hydrogen value chain. Once again, the production technologies there, the thermochemical routes, essentially from hydrocarbons, but not only. The electrolysis routes are given there, and also what we're hearing about in Alan's talk, from biological routes to hydrogen production. I'm sorry. And then in the center there, the storage of hydrogen, the distribution of hydrogen, and then the consumption in the various utilizations. So what I want to underline here is, well, first of all, a couple of things from the point of view of the use. Hydrogen can either be used as a feedstock chemical, so use in chemicals production in refinery, for green steel production, for fertilizer production. But it can also be used electrochemically, and this is what that says at the top there. This is the great advantage, essentially, of hydrogen, that we produce hydrogen, and it has this advantage for sector coupling either as a chemical feedstock or an electrochemical use. So if we use it electrochemically in a fuel cell, then we have access to the use of hydrogen for transport in essentially heavy-duty vehicles is what we're talking about at the present time. So things like trucks, but also shipping, fluvial uses, and rail. So on the one hand, the important points from an electrochemistry point of view are electrolysis of water using different electrolysis approaches that are indicated here, or the use of hydrogen in hydrogen fuel cells. So let's come back to that. So green hydrogen then is essential in the energy transition. Green decarbonized hydrogen essential in the energy transition. In order to produce that clean hydrogen, we are going to be using water electrolysis. Electrolysis then uses electricity to split water into hydrogen and oxygen. So reaction there on the left-hand side. And on the other hand, on the right-hand side, the fuel cell uses the opposite reaction. So a fuel cell uses the hydrogen and oxygen to produce electricity and water. So of those different technologies that are available, speaking about electrolysis first of all, for different high-temperature technologies, solid oxide technologies, or low-temperature technologies using polymer membranes, it's the proton exchange membrane fuel cell and electrolyzers that are most advanced at the present time. On the one hand, for transport application with PEM fuel cells, and on the other hand, for coupling with renewable energy resources with PEM electrolyzers. Now, the heart of a proton exchange membrane fuel cell or electrolyzer is what we call a membrane electrode assembly, which comprises a proton conducting polymer, which is what is indicated there in green in the middle, and then on the other side, the two electrodes, the anode and the cathode. And these anode and cathode usually have precious metal catalysts, noble metal catalysts. So that brings me to the challenge, essentially, because what I've done here is represented the Janus, which is the deity of duality. Because on the one hand, we have clean hydrogen as a key enabler for the energy transition, a sustainable chemical feedstock. That's what we were talking about. It's an essential component of the routes to net zero by 2050. And yet, on the other hand, we have to balance this with the fact that, as I just mentioned, in our proton exchange membrane fuel cell or electrolyzer, we're using a membrane material, which at the present time is most commonly a perfluorosulfonic acid. And it was Charlotte that mentioned earlier on this afternoon that perfluoroalkyl compounds are at the heart of a debate at the present time. These are everlasting chemicals, forever chemicals, and certainly there's a debate on them at the present time about the continued probity or whether or not we're able to use them. That's one point. The other point is that at the anode and the cathode, I mentioned the use of precious metals, noble metals, essentially in these technologies, platinum and iridium, and these are strategic or critical raw materials. So we have to ensure, on the one hand, that we are able to underpin the future development of hydrogen technologies, but we also have to do that by ensuring the sustainability and non-criticality of the kind of chemistries and materials and components that we're developing. So let's look at this in more detail, first of all, by looking at the membrane material in the proton exchange membranes, fuel cells, and electrolyzers. So the membrane material is essentially this perfluorosulfonic acid, this PFSA. It's an advanced solid electrolyte material that has the structure that's given up there in the middle. Essentially, two types of this PFSA material are developed at the present time. They both have the same polymer backbone that you can see there, and they differ in the length of the side chains that carry the proton charge at the end. The most developed of these at the present time is that from Solvay, so the equivalent material on the right-hand side. More developed because its particular structure there allows a higher temperature operation of the fuel cell or the electrolyzer. It has a lower gas crossover during the operation of the fuel cell or the electrolyzer, and that enables then a better, more efficient operation. So the current technology readiness level of PEM fuel cells and PEM electrolyzers is largely due, not only of course, but largely due to the exceptional properties of these membrane materials and these polymers. And really the technology would not be at the state where it is at the present time with commercialization, introduction and deployment and usage if we didn't have such materials as these. So I'm not really going to talk about our own work, but this is just one result of some results from a recent European project called Gaia that we coordinated from our labs in Montpellier. And in this we were able to, in fact, even further improve the stability of the PFSA Nafion equivalent type materials by developing particular kinds of stabilization chemistries, to the extent that we were able to apply what we call accelerated stress testing on these membranes, and which were able to withstand a very large number of cycles that you can see there, equivalent to more than 30,000 hours of operation, in this case in a fuel cell. And of course, anything that increases the stability, we were also working on overall improving the performance of the membrane electrode assemblies, while also reducing the amount of platinum. And all of these three considerations there then ultimately reduce the cost of the fuel cell or the electrolyzer material. And that, of course, is important as we go forward. But despite the advantages and the essential character, I would say, of these PFSA materials, they are the center of scrutiny. As I said, it's not only in the US and in Europe, but in Japan. Also, a lot of discussion about the use of perfluoroalkyl type materials, of which the PFSA is a member. So unfortunately, there's a kind of a generalized approach, bunching all of these PFSAs, if I may say, into the same bag, to the extent that the European Chemicals Agency has published about a year ago now a restriction proposal. And this restriction proposal would mean that once it comes into force, that there would be an 18-month transition period. And then after that, possibly a 5 or 12 years, what they call derogation period, but only for those sectors that have no slot-in ready alternative. And of course, that's true for many sectors. This would have an enormous impact on the future proper implementation of PEM technologies for hydrogen production and for the hydrogen end uses. And so it brings me to the point on the left-hand side there that should there be a restriction proposal which may come in 18 months or 5 years or 12 years, but undoubtedly at some point, then what are we going to be using as a replacement for this kind of polymer? So the obvious alternative, of course, if we're not allowed, as it were, to use fluorine chemistry anymore, then we're looking back at hydrocarbon alternative sulfonated hydrocarbon materials. There's already been a considerable body of work done on sulfonated hydrocarbons, looking back to the 2000s or so. There are some old publications of our own that are listed there. What I've done is just to gather together some kind of important properties in the context of fuel cell and electrolyzer application of the membrane material, and just comparing them, in fact, the sulfonated hydrocarbon materials, for almost each of those properties there come out to be inferior. So there's already a regain of interest in the development of sulfonated hydrocarbons, specifically for this reason. And undoubtedly this is going to continue in the future as the discussions continue on the possible restriction in the use of these fluorinated sulfonated materials. So moving on, I've talked about the membrane. I want to talk about what's used as the catalyst in electrolyzers and fuel cells. What's up here on the left-hand side is the relative abundance of all of the elements in the Earth's crust. So it's a relative abundance, so we can see the ones that are highlighted down there in the bottom in the yellow band are those that we'll be using in fuel cells and electrolyzers. Sorry, I've got fuel cells and electrolyzers, so platinum and iridium used for the electrocatalytic reactions, the anode and the cathode, electrolyzers and fuel cells, compared here to much more abundant elements such as iron, for example. So something like 10 to the power of 9 difference in relative abundance of these rarer elements compared with something like iron. So this is one consideration. It's obviously scarce, but also overall, in the particular case of iridium, there's only about 7 to 8 tons that are actually produced per year. This is really not very much compared with others. It would fit into about 7 cabin bags, the amount of iridium that's actually produced every year. The price is very volatile. You can see that there have been jumps in prices over recent years. So all of these factors, along with the fact that it's strategic as well in the sense that it's almost only produced in South Africa, all of these kind of add together to indicate that we must carefully look at where we can get our iridium from and how we can use it in the context of the ramp up of hydrogen production and increase in PEM electrolyzer capacity. So that's what this is showing here. Let me start on this side. So we need, for the energy transition, we need hydrogen to produce hydrogen. We need PEM electrolyzers to produce PEM, to produce PEM electrolyzers, we need to have sufficient iridium for the reaction at the anode. Currently on the right-hand side, to produce a 1 megawatt PEM electrolyzer, we will be using around about 400 grams of iridium. And so you can put that into the context of the 7 or 8 tons that are currently produced, in fact, every year. Now, on the left-hand side of the International Energy Agency are predictions and calculations and forecasts for the amount of installed PEM water electrolyzer capacity between now and 2050. And you can look at the numbers there in terms of gigawatts of electrolyzer capacity that are predicted and that will be required, in fact, for the global hydrogen production. So to what these numbers clearly don't match. So how can we make them match? Well, on the one hand, we have to clearly reduce the amount of iridium that we're using in an electrolyzer and make it perform much more efficiently in order to produce more hydrogen for the amount of iridium that we're putting in. There's already been good progress in that area, so we're currently down from about 400 grams of iridium for that 1 megawatt down to about 60 grams by using materials engineering approaches. There will be more materials engineering approaches. There'll be advances also in membranes, making them thinner, so that we produce more hydrogen for the amount of iridium that we're putting into the electrolyzer. But that won't be sufficient. Clearly, recycling is absolutely essential, and the calculations show that very efficient recycling, in fact around 95% of the iridium that is immobilized in the future electrolyzers must be recycled, so in a kind of a closed loop recycle to ensure that we have sufficient iridium to satisfy the future demand for the ramp up in PEM water electrolysis. Clearly, the recycling reduces the amount of new iridium, new mined iridium that we will be needing for the PEM electrolysis, but it also, because it balances supply and demand, it helps to stabilize also the iridium market price. Turning now to platinum. Platinum is also down there in the yellow band, so similar, if slightly, not quite as rare, but similar degree of scarcity as iridium. It's also a critical strategic metal insofar as, in fact, it's only produced, mined mainly in 2 countries. The big blue circle, part of the circle there, is production from South Africa and then production from Russia. And this is collectively around about 90% of the platinum that's produced internationally. So we're faced with similar kinds of issues. There's a lot of work being done, obviously, on reducing the amount of platinum that's used in fuel cells. Also, recycling is going to be essential as well, but in this particular case, there's also a lot of work done actually on replacing platinum at the cathode of fuel cells by using more abundant elements, and in particular by iron, atomically dispersed iron in particular. A lot of work done. This was a framework of another EU project that we ran on critical raw material electrocatalyst replacement, actually replacing platinum along with our partners there, including partners such as BMW. So even companies, large companies, looking ahead at the replacement of platinum in their fuel cells. Unfortunately, at the present time, the performance is just not there. So neither from the point of view of the activity, the performance, nor from the point of view at the present time for the stability are iron catalysts sufficient. But obviously they reduce dependence on critical raw materials, and so this once again is an area as we go forward where much more research is needed. I just want to finish up with this one. I've been talking about proton exchange membrane technologies and the associated kind of dual aspect of the issue of the fluorinated polymer, the use of platinum, the use of iridium. Not that these are showstoppers, it's just that we have to use what we know as chemists in order to reduce and ensure recycling. But there is an alternative, new emerging technologies, and Mark referred to this in a sense, by replacing the membrane instead of proton exchange membranes, using anion exchange membranes. These different kind of membranes, they're mainly hydrocarbon type membranes rather than fluorinated materials, so that helps in solving one of the issues, and also because of the different pH environment, we don't have to use precious metals, we can use non-PGM materials, non-precious metals, which are much more stable in this environment, so there's certainly an opportunity there. There are specific challenges of stability, in particular of the polymer material. There's the carbonate formation that Mark referred to. But there are definitely opportunities, as I was saying. There's been a lot of progress both on fuel cells and electrolyzers using anion exchange membranes, in particular electrolysis. But once again, there's more work to be done. I'll come back to what I wanted to do was talk very quickly about the hydrogen environment in France, if I may. I'm not going to say all of this. But I wanted to say a few words on French national strategy with regard to hydrogen. So French national strategy published last year with 3 priority areas: decarbonizing industry by creating a French electrolysis sector. So the use of that hydrogen then initially in developing heavy-duty mobility, and thereafter in using that hydrogen, and that's the third point there, in use of hydrogen as a chemical feedstock. So fertilizer production, ammonia, clean steel, the words that you can see there, but also supporting research, innovation, and skills development. So that point is developed at the present time through what is called the Priority Programme and Equipment, a programme in the area of decarbonised hydrogen, under which there are currently 19 projects that are running with 80 million of funding from French government in the different application areas, development areas that you can see there, going right the way through from production, storage to various uses. There's much more information you can find on that website if you're interested. And this program is jointly run by our national research organisation, CNRS, and the Atomic Energy Authority, the CEA. There is a national French network on hydrogen energy, which brings together essentially all of the labs in France that are working on hydrogen. This is run under the auspices, once again, of CNRS, different application areas, different labs that are involved, and our laboratory down there in the south of France, ICGM laboratory. You can also find more on the CEA Hydrogen Technologies Programme on their website there. We have a national association on hydrogen, France Hydrogène, which brings together all of the stakeholders. So this is large and small industry. This is also research centres, centres of excellence, competitiveness clusters, and local authorities, altogether 450 stakeholders in France under this national association, and a website with lots of information on hydrogen there. And just finally, looking at Europe and France's involvement in European funded projects. Yes, Alan just mentioned the so-called important projects of common European interest. And here French industry is involved in 10 of the 41 approved projects, and the various new factories that will be developed are shown on that map there. So factories developed in 7 different regions by that different French industry that's indicated there. And this really is the last slide, just to point out implication involvement in the fuel cells and hydrogen fuel cells and hydrogen joint undertaking and the clean hydrogen partnership or joint undertaking. So these joint undertakings that have been running at European level now since 2008, so more than 15 years or so. I have data here which shows the results from participation in Horizon 2020, so from the period 2014 to 2020, where actually France had a 40% success rate in the various proposals in which it was involved. And if on the right-hand side in that graph there, was actually leader in terms of the proposals that it coordinated. So that's good news, I think. People that decide these things were pleased with that. And it came second in terms of the amount of funding, 90 million funding obtained, so second in terms of getting funding from Europe in the fuel cells and hydrogen area, so second only to Germany in that. Okay, thank you very much. This was my absolute final one, where I just wanted to point out that the past in this field was the importance of deployment. So there was much less attention paid to the amount of platinum, the amount of iridium that we're using, the fact that some of these chemistries are environmentally not benign. That stage, I would say, is to some extent over. The future is going to be circularity by design, much more remanufacture, recycle, and environmentally benign chemistries. Thank you very much.
Thank you very much, Deborah. Thank you. Excellent talk.